Hi everyone, welcome back to Math 11. So in this section we're going to be looking at section 5.4, which is the normal distribution. So a normal distribution is basically a histogram that once you stack all the bars next to each other, it's going to look like this pattern shown right here. So even though the bars are not shown, because this is just the outer shape of this is called the normal curve, so it does not show the actual histogram bars. Now this is also known as aka the bell curve because it resembles a bell. And also the person who actually came up with it, it's also known as the Gaussian because Gauss is the physicist, mathematician, German scientist who actually came up with it. So it's called the Gaussian. That's probably the proper name for it. So the Gaussian curve. And this particular curve, the reason we learned this in high school is because it's a very, very common type of distribution. So you're not going to just see it in math, you're going to see it all over the place. You're going to see this in any social sciences like sociology, anthropology, psychology, criminology. So it doesn't matter whether you decide to study science or not, you will probably encounter this normal distribution somewhere. So that's why we learn about it at least a little bit. We're not going to be getting into the equation for it or anything like that, but we need to understand it at least. So again, the curve itself is the outer shape. If you start adding the histogram, let's say you add the bars, then this becomes a normal distribution. Okay, so the mean of any normal curve or any normal distribution is going to be right in the middle. So this is going to be your, depending on what you're looking at, are you looking at the population mean or are you looking at the sample mean? So this can be either your x bar, which is your sample mean, or it could be your mu, which is going to be your population mean. So the mean is always going to be in the middle. So it says here, notice the majority of the data of the points are close to the mean, which again, most of the points are right here, right in the middle. We say that data is normally distributed if the graph data looks like a normal curve. When we have data that is normally distributed, that means that the central tendency should be all similar or the same. So if you remember, the central measurements, central tendency measurements are your mean, median, and mode. So if the data is normally distributed, so all three of them are going to be equal or at least very close to each other. So the mean, the median, and the mode are going to be all very similar to each other. And again, they're going to be right in the middle. So there's a lot of data that follows this pattern. So one of the common examples is IQ scores, which goes from 0 to 100%. So most people fall somewhere. The mean is supposed to be 100% or 100 points. I don't know what they actually use for the scoring. I think it's just points. Other things that follow the same pattern is people's weight and height. So weight and height. So if you take all the people in the world and you measure their height or their weight, you're going to see that most people, so they're going to follow the same curve that we see here. Blood pressure is another one. So some people have high blood pressure, some people have low blood pressure, some people have normal blood pressure. So the word normal actually comes from statistics from the normal distribution. So normal means that you fall right in the middle here. That means that you are normal because you're within the center of this distribution. What else? So we have IQ scores, weight, height, blood pressure. There's a couple more. I have monthly average temperature differences. Some monthly average temperature differences. And quality control. So for example, when you're checking for quality, let's say we have an assembly line of something, of some sort of product, most things are going to be good quality. Some of them going to be really good quality, which is going to be on the right side. Some of them going to be rejects, basically they're not good enough because something is wrong with them. So most of them, again, is going to be in the middle, so they're going to be normal. So quality control follows normal distribution as well. So there's lots of examples that can come up here. And again, that's the reason why we learn about this, because you're going to see this curve, or you're going to see mentions of the bell curve, or the normal curve, or the distribution all over the place, not just math. So quality control is the last example that I have for you here. So again, since we're just learning about what this means, how we can use it, we're not going to get into the equation for it because you need to know some calculus. So we're going to learn some rules, some empirical rules that we can use. Before we get to that though, there's a couple of definitions that I should mention here. If you look at this graph, we have some Greek letters at the bottom. Now, if you remember from last video, we have letter sigma, which is a Greek letter, and this means standard deviation. Okay. Now we have another letter, letter mu, which is like the Greek letter M, but instead of writing the way we do in English, we write like this. So it's kind of like an M like that. So anyway, that's going to be letter mu, and this stands for standard. For standard. This stands for the mean. Actually, it stands for the population mean. So to be more precise, this is population mean. So remember, I made the distinction between the sample and the population. So sample is just a small portion of the population. Okay. So the mean of the population is if you take the whole population and you look at the average in the whole population, and the X bar, if you remember, this is the mean, but we use this notation for the sample mean. So you're gonna see these notations. So X bar is the sample mean, mu is the mean of the population. So that's just the difference between different notations. Sometimes we just write SD for standard deviation of the sample. So again, that's just different notations. So anyway, the point I was trying to make is that sigma, again, is your standard deviation, mu is the population mean, or just think of it as the mean. So what does this mean? If you have normal distribution like so, and if you look here, this is our mean, mu, and then we have mu plus sigma, and then mu minus sigma on the left side. So mu plus sigma means the mean plus one standard deviation. And then mu minus sigma means the mean minus one standard deviation. And the area between the plus minus one standard deviation, so each one standard deviation to the left or right is 34%. So if you take this total between plus minus one standard deviation, you're going to get 68%. So if you add 34 plus 34, you're going to get 68. So that's the pattern that we should remember from this diagram. So if you go plus minus 1 sigma, or one standard deviation left and right, you're going to get 68% in total. The percentage, I mean the area under this curve. So if you, again, go from -1 to +1 standard deviation, you look at the area under here, this is going to represent 68% of the total area under the curve, which is 100% in total. Okay? So plus minus 1 sigma is 68%. And then if you go one more standard deviation to the left and right, you're going to go mu plus 2 sigma and then mu minus 2 sigma. So we're adding 2 standard deviations left and right. So if you go 2 steps or 2 sigmas, now 34 plus 13.5 is going to be the total that you see for this area, which is, what is it going to be? 34 plus 13. 34 plus 13.5 is going to be 47.5%. So for example, if you go 2 standard deviations to the left or to the right, that's going to represent 47.5%, which is almost half, right? So if you then go plus minus 2 sigmas or 2 standard deviations, you're going to end up with 13.5 plus 34 plus 34 plus 13.5. So That means that we're covering pretty much almost all of it, which adds up to a total of 95%. Okay? So if you add 47.5 plus 47.5, you get 95%. And then, of course, if you go 3 standard deviations, so let me erase all of this. If you go now mu, which is our mean, then you go 1, 2, 3 sigmas, so you get mu plus 3 sigma, so that's 3 standard deviations to the right, and then you go to the left 1, 2, 3 steps. Now you have mu, it says minus 3 sigma, which is 3 standard deviations to the left. We end up with a total of plus minus 3 sigmas, which covers pretty much the whole curve, right? We started from here, we're gonna use all of this, all of this, all of this, all the way to plus 3 sigma. And this whole area, if you add all the percentages, 2.35 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35, we get 99.7%. So within the plus minus 3 standard deviations, you cover pretty much the whole surface of this area under the curve. Now, if you go further, you go with the 4 standard deviations, it's just going to be pretty much in the hundreds or the thousands now. So normally what we use is those 3 standard deviations for most things. And actually, this is called the 64-95 99.7 rule. Okay, so that's one thing you're going to remember, or you will have to remember for this statistics course, basically, or this section really, is that rule. That's one thing we need to know, because this will help you answer a lot of the questions without doing a lot of the math. So, like I said, this is something you're gonna see in your, like I said, you're probably gonna see this in psychology or a lot of the social sciences, and you're gonna learn the same thing again. You're gonna learn about this statistics, which is basically just the basics, just to understand how this curve works. So what can you do with this curve? So we know this rule 64, 95, 99.7%. So how can we use this? So let's take a look at an example. So on the next page, we have the first example. And this says, based on the normal distribution curve, find the percentages between the mu, so that's the mean, to the mu plus 3 sigma. Okay, which means if you look back at our diagram here, we're going to go from the mean, so for our mu, for starting here, all the way to plus 3 sigma. So plus 3 sigma. So we're going to go from here all the way to here. So we need to find what is this area from the mean to the right, mean plus 3 sigma. So that's going to be 34% plus 13.5% plus 2.35%. So that's what the area is going to represent. So we're going to write here that this is going to equal to 34 plus 13.5 plus 2.35. Okay, so when you add this, we get 34 plus 13.5 plus 2.35. In total, we get 49.85. So almost 50%. All right, so that's from the mean, from the middle, to 3 standard deviations to the right. So let's take a look at another case. This one says from mu minus sigma, which means 1 standard deviation to the left, to mu plus 2 sigma, which means we're going to go 2 standard deviations to the right. So in this case, we're looking starting from here. So we're starting here, and we're going to go plus 2. So we're going to go all the way to here. So now we're looking at all of this area here. Right? So we're starting from here to here. So we have 34 plus 34 plus 13.5. So that's going to be our B part. So it's going to be 34 plus 34% plus 13.5%, which in total, so 34 plus 34, that's 68, plus 13.5, it's going to be 81.5%. Okay, and then let's do the last one, which is going to be C, which starts from negative, so mu minus 3 sigma, which is on the left side, so 3 standard deviations to the left, to mu plus 1 sigma, which is 1 standard deviation to the right. So let's take a look at our graph here and help us figure this out. So again, we're starting from negative 3 right here, right? And we're going to positive 1, so plus 1 sigma, which is going to be here. So now we're looking at all of this area. So it's going to be all of this. So we're going to add the 2.35 plus 13.5 plus 34 plus 34. So that's going to be the total area that's covered between those two values. So here we're going to have, let's see, 2.35 plus 13.5 plus 34 plus another 34. So again, 34 plus 34 is 68, plus 13.5 is 81.5, plus 2.35, we get 83.85%. So between those 4 standard deviations here, we get 83.85. Okay. So that's one example where we just use the 64.95, not 64, 68, sorry, there's a mistake here. It should be 68 because 34 plus 34 is 68. So that's how we can use the 68, 95, 99.7 rule to answer simple questions like these. When we're given the values for the mean and the standard deviations, you can actually answer it just in percents. Now, the next question, it says, suppose they have data that is normally distributed with the mean of 52.5 and sigma 2.4. So it says here, draw distribution of the data. So notice here, we're given the mean, actual value. Before we're just given mu, no value at all. Now we're given the values for both the mean and the standard deviation. So we're gonna draw the curve here. So roughly it's gonna look like this. So we're gonna have our curve. So right in the middle, this is gonna be our mean, which is gonna be 52.5. Okay, so we're gonna split this into 3 standard deviations like before. We're gonna do plus standard deviation, plus 2, plus 3 standard deviations. And the same thing on the left side. So minus 1, minus 2, minus 3. Now, because we know the value for sigma, we can actually calculate the actual number that's gonna go here on the x value. So I don't know what these values represent. It just says data, so we don't know what these are. But we can actually calculate it. So for example, you can do your mu plus 1 sigma, which is going to equal the 52.5 plus 2.4, which is going to equal 54.9. And then we can do mu plus 2 sigma. So that's going to equal the mean, which is 52.5 plus 2 times 2.4. And this equals to 57.3. So we multiplied 2 times 2.4 and then added the mean. Let's do one more. Let's do mu plus 3 sigma. So we keep going to the right. So this is going to be 52.5 plus 3 times 2.4, which is going to be 59.7. So those are all the values on the right side. So these values are going to go here. So let me just extend this line so we have space to write the numbers. So this is going to be 54.9. This one here, this one is going to be 57.3. And the 3 standard deviations away is going to be 59.7. All right, so we can do the same thing on the other side. We can do the negatives one as well. We can do mu minus 1 SD, which is going to be 52.5 minus 2.4, which is going to be 50.1. We can do mu minus 2 sigma, which is going to be 52.5 minus 2 times 2.4, and this equals to 47.7. And let's do the third one, minus 3 sigma, which is going to be 52.5 minus 3 times 2.4 equal to 45.3. So those values are going to go here. So again, let me extend this line a little bit. So this is going to be 50.1. Then this guy here is going to be 47.7. And at the bottom we have, or furthest to the left, we're going to have 45.3. All right. So why would you do this? Well, now we can actually answer questions like the ones that it's asking us in part B. Because we actually have values for mu and sigma, we can now get the answers. For example, what percent of the data is between 47.7 and 54.9. So for part B, we're looking at values between 47.7, so starting here, all the way to 54.9, which is going to be all the way to here. Now, this area here, this corresponds to 1 standard deviation to the right. So we know this is going to be 34% from 52.5 to 54.9. And then 2 standard deviations to the left. So this is going to be another 34%. And then we're going to have, if you can go back here, then we're going to have another 13.5 to the left. So if you break this into segments, so let me use a couple of different colors so it's easier to see, like so. So remember, here we have 34%. This area here is 13.5, and this is 2.35%. Another 34, 13.5, and again, this is 2.35%. Okay, so to answer question B, we're going to add, going from 47.7, which is 13.5, plus 34, plus another 34. And this is all in percent. So we're going to get 81.5%. So what percentage of the data is between 47.7 and 54.9? Well, it's going to be 81.5%. So the area under this curve corresponds to 81.5%. Now, part C says, what is the percentage of data less than 45.3? Which means that 45.3 is way down here. So if we look at this diagram, we're talking about this area to the left. Less than means to the left, right? So we're looking at less than 45.3, which is less than 3 standard deviations to the left. So the whole area is 100%, okay? So if the whole area is 100%, then all we need to know is this little bit here. Well, we know if you have plus minus 3 standard deviations, it's going to be 99.7%. And then we're going to be left over with the left and the right side, which is going to be the leftover area, which is going to be like 0.3%. So then we can just divide it by 2. Or actually on this side, on the diagram that was shown here, we're actually given the values. So each area here corresponds to 0.15%. So we can add that to our diagram and say, well, we know that this remaining area is 0.15%. So is the area on this other side, which is also 0.15%. So to answer this question, you can say, well, it's just going to be 0.15%. Or if you actually wanted to do the math, you can do the following. You can do the calculation. If you just remember this, if you just remember the rule, the 68, 95, 99.7 rule, then you know that 3 standard deviations plus minus 3 standard deviations is going to be 99.7. So you can say, okay, 100% minus plus minus 3 standard deviations is going to be then the 99.7. And then that's going to, again, correspond to the left and the right parts, which are past the 3 standard deviations. And then if you divide it by 2, you're going to get the same answer of 0.15%. So again, you could have done it either just by looking at the previous page or actually calculating it this way. So using the rule. So that's about it for the standard deviation with the curve, with the bell curve. Now I do want to show you how to do this using Desmos, because Desmos has really powerful tools for this. So if you go to the web page, Desmos graphing calculator, or again, if you get the app for it, either one works fine. So here I am at, again, desmos.com/calculator, and if I click on show keyboard, click on that, and then I go to functions. Now I'm going to go to, before we use statistics, so in the previous section we used standard deviation, this one right here. Now we're going to go to distribution, so dist, and I'm going to click on the normal distribution. Okay. Now there's other distributions here that you might learn. Again, if you take calculus in college, you're going to learn about the Poisson distribution, the binomial distribution, but we're only concerned about this one, just the normal distribution. So you're going to click on this one, and it's going to give you the name of the function, so later on you can just type it in. And it says normal distribution, open parentheses, and then it says mean, comma, standard deviation 1. So what you need to do is enter the mean and the standard deviation. So I'm going to do question number 2 using the graphing calculator here. So the mean in the question was 52.5. So again, if you go back to the question, the mean here is 52.5, and the sigma is 2.4. So I'm going to enter those values. So again, type in the 52.5, comma, and then enter the sigma, the standard deviation value, which is 2.4, and then press enter. So it seems like nothing happens, right? You look at your graph, we can get rid of the keyboard now, and it's just a red line. So what you need to do next is you're going to go to this little zoom fit. You're going to click on this, and it will zoom to your curve. Because it was zoomed out, so you couldn't really see it because it was so small. So once you press on the zoom, it will zoom into the curve, and as you can see now, the middle is our mean 52.5. So if you wanted to add, let's say, a vertical line just to see x equal to 52.5, it's going to be right where the middle of this curve is. So what else can we do with this? So how can we use this function here? So if you look here, it says find cumulative probability. So that's the percentage. So remember, probability is measured in percent. So that's the area under the curve. So you click on this, you check the box, and now it shows the whole area shaded, which corresponds to 1 or 100%. So right now it goes from infinity to infinity, so from negative infinity to positive infinity. So we can do part B, which the question says, what percentage of that is between 47.7 and 54.9? So we're going to do it, we're going to enter the left limit, so 47.7, so 47.7. And right now it shows, if you just enter 1, it will show from 47.7 to all the way to infinity on the right, so all the area to the right. But then if you enter the right boundary, which is 54.9, it's going to show only the area between those values. So as you can see, it shows the area that's shaded in red, only between 47.7 and 54.9. And if you look here, the answer is in a decimal form, but you can convert it to percent by multiplying by 100. Right now it's showing 81.85, so basically 81.85%, and that's the answer that we got in our case. So if you look here, part B, we got 81.5, so I rounded to 1 decimal. This one shows a lot more decimal places because it's a lot more accurate. But again, as you can see, you can get the same answer just using the graphing calculator. So let's do part C. The part C says, what is the percentage of data less than 45.3%? So let's clear this. Let's get rid of that and get rid of this. Okay, so again, once you remove the boundaries, it will go back to 100%. The whole area is shaded. But now it says less than 47.3. So we're looking for the values left of this value. So which means that the maximum value has to be 45.3 here in order for this to show us the right area. And as you can see, it's so small, it doesn't really show. You can try to zoom in here to see it better, but this area is so tiny, right? It's hard to see it. So this area right here is this number right there. Okay? So as you can see, this number is not exactly the same number that we got, unless I entered the wrong, no, it looks like the right value. But because we're using kind of empirical rule, the 68, 99, 95, 99.7 rule is not as accurate as this. This is a lot more accurate. So if you're using the z-score table, which we're going to learn in the next couple of sections, or you use the graphing calculator, it will give you much more accurate answers. So this one is a little bit more accurate. My answer was 0.0 0.15%. So remember, this is not in percentages. What you see here in Desmos is in decimal form. So you have to remember to multiply by 100. So you're going to get 0.13%, right? So it's going to be 0.13%. The answer we got here is 0.15%. So it's a little off, but again, just because we're using the rule, we're not using graphing calculator. So if you are using graphing calculator, like again, Desmos here, you're going to get a better answer. So as you can see here, it's really easy to do this with the graphing calculator. All right, so for homework, there's a few practice questions, and for some of them, you might need to use the graphing calculator in Desmos. So again, all you have to do is go to the keyboard, go to functions, distribution, click on the normal distribution, and then you're able to enter more values. You can have multiple distributions shown as well. All right, so again, for homework, let's see, we have chapter 5, so this is section 5.4, so make sure you read through the examples, pages 241 to 250, and do questions 1, 4, 8, and 13. For some of them, you might need to use Desmos. Again, if you have any questions, make sure you post them as replies in Teams.